So in the last recording, we did cover the quick scheme or the parabolic quadratic upwind differencing scheme, which known as quick scheme. It's time now to go through an example to see how we can apply this scheme here. So I'm gonna go back to the one-dimension example model. I have phi A equal 1, phi B is equal 0. Then we were given that rho is equal 1. That's the same example that we covered with the other schemes before. So it makes it easy to compare the results every time you change the conversion, the approximation scheme, and see how the conversion looks like. A is also 1, kappa is 0.1, and delta was selected to be 0.2. The velocity in this case is the 0.2 meter per second. So these are the information from the previous example. Now I would like to get the distribution at 0.2, which means that I have 5 cells. Let's note the nodes, 1 through 5. And we would like to use the quick scheme to solve that problem and get the distribution here. So I will, as usual, I'm going to start with the interior node. So number 1, I'm going to look into the interior nodes 2, 3, and 4. If you draw a schematic for these interior nodes, you will have P, you will have east, and you will have the west node. Here is the east face, and this is the west face. As we explained before, in the quick scheme, you need 2 upstream nodes. If the flow is going this way, that's the positive direction of the flow, which means that I need 2 upstream nodes, right, for that face. So for the east face, I have already 2, and 1 downstream, which is E. When I go for the west face, I'm going to need another node, which we call it west-west, and the downstream would be the point P. So just as a reminder for how we did the scheme. Again, you start from the general transport equation. You do the integration over the cell volume, then use the diversion theorem to convert the integration over the control volume to the integration over the control surface boundaries, and you end up having F east phi east minus F west phi west equal to kappa east A east d phi by dx on the east minus kappa west A west d phi by dx on the west face. This is the general equation. Again, all what we are trying to do is to approximate the value at the face by the unknown values of the nodes. That's simply what we are doing here. So we know that d phi by dx, that's a diffusion term on the east face. This is where we assume everything is changing linearly, right? So I'm going to have for the diffusion term, this is phi E, this is phi P, and this is phi W. And we are trying to get the value of d phi by dx on that east face, which is the slope of the line. So this would be simply phi east minus phi P divided by delta x east. If I want to get d phi by dx on the west face, this would be simply phi P minus phi west divided by delta x west. Now the approximation for the convection term, phi east and phi west, for the quick scheme, we know that phi at the face is simply equal to 6/8 phi I minus 1 plus 3/8 phi I minus 1/8 phi I minus 2. So you pick up the face, you're gonna label the next point is I. If I'm looking for the east face, I'm gonna call this I. This is I minus 1, and this is I minus 2. So if I wanna get phi for the east face, will be simply 6/8 phi I minus 1, which is gonna be phi P plus 3 over 8 phi I, which is phi east, minus 1 over 8 phi I minus 2, which is phi west. If I want to go for the west face, this will be I minus 1. I'm going to use a green writing here, the pen. This is I minus 2, and this will be actually my I. So if I'm looking for phi on the west face, will be simply 6 over 8 phi I minus 1. For the west face, I minus 1 is going to be phi west, plus 3 over 8 phi I. Phi I for the west face is going to be phi p, minus 1 over 8 phi I minus 2 is going to be phi west-west. Then I'm going to take these two equations and these two equations and substitute into this equation. This is classical procedure like what we did when we were driving the, after we drove the quadratic equation and we substitute into the equation. You will substitute, you're going to end up having the big equation that we covered before, which is AP phi p equal to A west phi west plus A east phi east. And I don't think so. We're going to have, there is no source term, right? So maybe we're going to have SU as well, right? Maybe we did miss that in the previous case, but here we will have that because of the WW. So let's see how far we're going to go with this. Let's substitute in the equation and see what the final form would look like. The final form, you substitute, you should end up having the following. I would have d west plus 6 over 8 if west plus 1 over 8 if east, that's one term, plus d east minus 3 over 8 if east, plus the second term, plus if east minus if west. This is totally multiplied by phi p. This will equal to this is going to be my A west. This is going to be my A east. And this will be my minus SP. On the right-hand side, you will find yourself having D west plus 6 over 8 F west plus 1 over 8 FE multiplied by phi west plus DE minus 3 over 8 FE phi east. Then you will find an extra term, which is minus 1 over 8 F west phi west-west. So again, this is going to be my A west. This will be the A east. And this will be actually the SU term. So if I write down here, A west is equal to D west plus 6 over 8 F west plus half. 1 over 8, that's FE. Then I have A east is equal to D east minus 3 over 8 F east. I have, this is for the continuity is going to be 0, so SP is actually equal 0, right? And SU is equal to minus 1 over 8 F west phi west-west. Then you add up all these terms here, you're going to get actually AP is going to be simply A west plus A east, which is going to be simply the summation of these two, right? So we know that D east and D west are equal. That's going to be D, and we know that F east equal F west is equal to F, right? G is kappa A over delta, and F is the rho U. Let me recap that. So F is simply the rho U times A. I'm just recapping the number here. So kappa in the problem was given by 0.1, and A is given by 1. and delta is by 0.2. So we have D is equal 0.5. Then we have F is equal, rho is given by 1. U is 0.2, and the area is 1. So I got F equal 0.2. Just in case, we can calculate actually the Bickley number, right? Which is that F over D, right? That's what we covered last time. That's F over T over F, right? I'm just trying to remember that here. F over D, F over D. So we have 0.2 divided by 0.5. So we have 2 over 5, that's 0.4. That's the Bickley number. So let's calculate that. This would be simply as numeric value. I have these numbers already calculated, so I will just recall the number instead of doing math calculation right now. So I can simply say this is 6 over 8, 7 over 8, so that's actually D plus 7 over 8 F. Then this will be D minus 3 over 8 F. Then this is 0. This will be minus 1 8 F time pi WW. Then this will be the summation of these two together. So this will be actually 2D. Then actually 7 minus 3, that's going to be 4 over 8. That's going to be plus F over 2. So these are the coefficients for interior node. But you have to be careful here when you look to the domain. This is very important. We usually have one equation that applies for all the interior nodes, right? So that's 1, that's 2, that's 3, that's 4, that's 5. That's not true in the case of the quick scheme. Because now, if you pick a point, you're going to need 2 upstream nodes and 1 downstream node. So if I pick point number 4 as an interior node, right, I will have 3 and 2 as an upstream nodes, and I have 5. 3, I have 2 nodes here, but I don't have 1 for number 2. So this equation actually is valid for nodes 2 and 3. 3 and 4. Which means that I have to treat node number 2 slightly different, because when I look to the upstream nodes, I don't have a second node. It's going to be in the middle of nowhere. So now we break down even the interior nodes into 2 groups. The first one is for node number 3 and 4, and now we need to find a solution for node number 2. So if you recall back the derivation of these coefficients, these are the same coefficient that we got before. I think we, by mistake, I wrote that SU is equal 0. It's not really equal 0, right? It's actually equal minus 1 over 8 FW. I remember during the derivation of the equation, I assumed that's going to be 0, but it's obvious it's not going to be 0. That's my SU. So I corrected that in the paper here. So now we need to look into node number 2 and how we're going to actually derive the equation for node number 2 and what we're going to do to find that second upstream nodes that don't exist actually here. So now, instead of saying interior nodes 2, 3, and 4, I excluded 2 right now. So we've done 3 and 4. Now we need to have a special title for node number 2. That's going to be step number 2. Okay, now number 2 is node 2. So I will assume this is node 3, this is node 2, and this is node 1, and there is a boundary here. That's phi A equal 1, and this is the first cell, second cell, third cell. I'm looking for node number 2. So that's going to be P. That's going to be the S east. This will be the W, but now W does not exist. It's in the on the air, so we cannot do anything with this. Let's see how we're going to do it. Again, I'm going to have the same equation: F east phi east minus F west phi west equal to kappa east A east d phi by dx on the east face minus kappa west A west d phi by dx on the west face. This is my east face, this is my west face. So for the diffusion term, d phi by dx on the east face will be phi east minus phi p divided by delta x east, right? This is a linear change here. That's phi east, that's phi p, and that's phi west. So I can get the slope by phi east minus phi p divided by delta x e, and d phi by dx on the west face of that point P will be phi P minus phi west divided by delta X west. No surprises here. Diffusion is always straightforward. There is no tricks. It's only one discretization scheme that we use, which is the central differencing scheme. Now let's go for the convection term. Now I'm going to apply the same equation for phi phase, and you will have that phi phase it's equal to 6 over 8 phi I minus 1 plus 3 over 8 phi I minus 1 over 8 phi I minus 2. So now this is my I. This is my I minus 1. We are in the east face, right? So we are on the east face. So if we are in the east face, this will be actually I. This is I minus 1, and this is I minus 2. So for the east face, I will have the equation as phi east is equal 6 over 8 phi p plus 3 over 8 phi east minus 1 over 8 phi w. So that's for the east face. Now I want to do the equation for the west face. So let me draw that here. This is P. This is the west face, right? I have one node before, that's the west node. Then I have the boundary, which is phi A is equal 1. And there is no WW. It's not physically exist, right? So this will be the I. This would be the I minus 1. And this hidden one is I minus 2. Okay? So how we're going to use that equation to write the equation for the west face? Since there is no actual physical exist WW, I'm going to call that node O just to make it distinguish here, because it's not physically exist. So there is no west-west node actually. I'm going to call it O and leave it that way. And let's apply this equation. So phi face, which is phi on the west face, as W small, equal to 6 over 8 phi I minus 1, which is going to be phi west, plus 3 over 8 phi I is going to be phi P, minus 1 over 8 I minus 2, it's phi O, right? I'm going to keep it that way, phi O. Now, how are we going to replace that phi O by something else that we are familiar with? I don't know what's the value of phi or the function phi on O. So the simplest approximation, we assume that phi at the interface A is simply the average of phi O plus phi W divided by 2. This is an assumption, as if we are using actually the upwind scheme, okay? Something like that. So I can get phi O out of this equation to be 2 phi A minus phi west. Now I can take this into this equation. So phi on the west face will simply 6 over 8 phi of the west node plus 3 over 8 phi p minus 1 over 8 multiplied by that. So it's minus 1 over 8 times 2 phi A, which is a known value, minus phi west. So now I got this equation, I got this equation, I got these two equations. I can take them and go back into the main equation and substitute to drive the equation. If you do that, you will get the final form as follows. You will get dE minus 3 over 8 FE plus dw plus 7 over 8 fw. These are w small, e small, plus 1 over 8 f east plus f east minus fw minus 1 over 4 f west. This is total term multiplied by phi p. That should equal to the following: dE minus 3 over 8 fe times phi east plus dw plus 7 over 8 fw plus 1 over 8 fe times phi west minus 1 over 4 fw phi a. Remember, I should have a term of phi a, and this is square that's coming from here, but that phi west is multiplied by f west. That's why we got f west here. So looking to these coefficients here, this looks similar to this. So this is simply a east. This is my a west. This is again my a east. This is my a west. This will be 0, so that's going to be simply my minus sp, and this will be my su. And you add up the 3 terms here, you're going to get actually the ap. So if I write down these equations or these coefficients, I would have, for node number 2, I would have a east is equal to d east minus 3 over 8 fe, which is going to be d minus 3 over 8 just f. Then we have a west is equal d west plus 7 over 8 f west plus 1 over 8 f east. Now f east and f west are the same. This will give me d west plus f, which is going to be 8 over 8. Then I have su is equal minus 1 over 4 f west phi a, which is going to be minus 1 over 4 f times phi a. Remember, we got before the value of d and f, right? D is 0.5. Keep that in mind. And f is 0.2. Then I will got sp is equal 1/4 over times f west, which is going to be 1 over 4 f. Then I will get ap is simply adding up this term and this term and this term. You add up these two. This is going to be just d. So this would be 2d. 1 minus 3 over 8f is going to be plus 5 over 8f. Then I have another minus 1 over 4 f. So this is going to be 2 over 8. So it's going to be 3/8. 2d plus 3/8 f. And these are the coefficient for node 2. Next, I finished these nodes here. I need to go for node number 1 and node number 5. And these are the boundary nodes. It's time for step 3. That's node 1. So let's plot that node 1. I have node 2, and here's node 3. I don't need it actually. So that's my P. That's my east, right? And I have the east face, and the west face is here. And phi A is equal 1. Okay. So what about the diffusion term? I know that for this case here, d phi by dx on the east face will be phi east minus phi p divided by delta x east. The second one will be d phi by dx on the west one. Now I'm looking for the slope of the line. That's phi P, that's phi east, and I don't have a west node, right? But I have phi A in here. So d phi by dx in the west face would be simply phi P minus phi of the face A, but this distance here is not delta x like this. This is delta x node, as we used to call it. And we know that delta x node is half delta x. So this is for the diffusion term. Now we need to do the convection term. So I'm going to put the equation for phi face is equal to 6 over 8 phi I minus 1 plus 3 over 8 phi I minus 1 over 8 phi I minus 2. Remember, I'm looking for the east face. So this is going to be node I. This will be I minus 1. And the I minus 2 will be the imaginary node that we call it O. That's when I do the east face value. So phi of the east face will equal 6 over 8 phi P plus 3 over 8 phi east minus 1 over 8 phi O. And we said that phi of the face A is an average of phi O plus phi P divided by 2, right? That's what we approximated the function with. So I can write down that phi O is simply 2 phi A minus phi P. Then I'm going to substitute into this equation. Then you're going to end up having phi of the east face is equal 6 over 8 phi P plus 3 over 8 phi east minus 1 over 8 multiplied by 2 of the phi A minus phi P. If you distribute that and you simplify the equation, you will end up having phi E actually equal the following. It's going to be 7 over 8 phi P plus 3 over 8 phi east. Then I would have minus 2 over 8 phi A. So I will border these two for the diffusion. I border that for the east face. Now, what about phi west? What is the west face for node number 1? The west face is simply that face A. So phi west for this case is simply phi A. That's actually much easier than node number 2. So now I got the 4 approximations. I will go back to the original equation and substitute, and let's see how the equation is going to look like. So now we got the approximation here. Let me write down d phi by dx on the east face. We said this is going to be phi east minus phi p divided by delta x east. Then we said d phi by dx on the west face would be simply phi p minus phi a minus divided by delta x node, right? This is what we used to do when we solved the diffusion problem, right? The issue is the quick scheme doesn't like to have that linear change near the boundary when there is a diffusion value on the interface. So this actually approximation is not allowed in quick scheme. So now quick scheme, which means that we have to find a different way to define d phi by dx, the diffusion with the interface, near the interface or the boundary for the quick scheme. So how actually the quick scheme is solving this problem? Quick scheme doesn't like to have in a linear change when you have a boundary condition involved here. So let's throw that issue here. We have that's node 1, which we call it P, and that's node 2, which is my east 1, and this is phi A here. And our problem now is to find a replacement formula for d phi by dx on that west face, which is right here. So since the quick scheme is using quadratic formula, he doesn't like that approximation here. So the approximation here is accepted for separated nodes by full delta x, right? But when it comes to delta x node or a shorter distance, the quick scheme is recommending to develop a quadratic equation between the west face, the P, and the E point. So how this would happen? So he wants us to do the following, to find a second order equation between phi east, phi P, and phi west. So you need to develop that quadratic equation. Then if you got that function, you're gonna get the derivative on the west face. I'm gonna assume there's an x direction here. So this x here is equal 0. This x is equal delta over 2. And this x here is equal to 3x, 3 delta over 2. And go back to the way that we developed the original quadratic equation, that phi as a function of x is equal a x squared plus b x plus c. If I take the derivative d phi by dx, what are you going to get? I'm going to get 2ax plus b. Now I want to get the derivative at the west face. What is the x coordinate for the west face? It is 0. So this is at x equals 0. If you put x equals 0, so I need b, and b will be actually the dw by dx in the west face. So that's one of the major differences between the previous schemes. This is the first scheme that really put a condition or restriction on the use of the central differencing scheme at a boundary node or a boundary face. So keep that in mind. This is one major difference between all what we did before and this one. Now, it's not only proposing the approximation for the convection term, it is also impacting the diffusion derivative or the slope of the function phi near the boundary edge. You have to develop that equation for it. So this is very special case here. So let's see how we're going to derive this equation. At x equal 0, I know the phi at x equals 0 is actually phi west. It's phi a, sorry, it's phi a. That at x equals 0, it's phi a. At x equal delta over 2, phi at x equal delta over 2 is simply phi p. And at x equal 3 delta over 2, phi at that value is phi east. Then you substitute into the equation, so you can actually find that quadratic equation. From this, I got the b coefficient, which is d phi by dx, which is going to be the b. I got my b based on my solution, b, which is d phi by dx on the west face is equal b is equal to 1 over 3 delta, then 9 phi p minus phi east minus 8 phi a. So this is now my d phi by dx on the west face. So I would say this is number 1. This is number 2. And these are number 3 and 4. You're going to take these 4 equation and go into f east phi east minus f west phi west equal kappa east a east d phi by dx on the east face minus kappa west a west d phi by dx on the west face. Now we're going to substitute with these 4 equations into this formula and see what the final result looks like. So I will substitute with f east multiplied by phi east, which is 7 over 8 phi p plus 3 over 8 phi east minus 2 over 8 phi a minus f west phi west, which is simply phi a, equal to kappa east, A east, d phi by dx on the east, which is going to be phi east minus phi p. I will divide by delta x east. It's going to be outside here. Then I would have minus kappa west, A west, d phi by dx on the west, which is the b coefficient that we got. So this is over 3 delta. And this will be 9 phi p minus phi east minus 8 phi a. This is the full equation. Now we need to separate the terms. So we know that this is d, right? Kappa a over delta is d, but now this is not d, right? So this also will be d, right? So I'm going to end up having the final equation. Looks like the following here. I'm going to have the following equation here to be sure I'm writing that correctly. So if you collect the term, you're going to have 7 over 8 Fe plus DE plus 9 D over 3 phi P is equal to D over 3 minus 3/8 Fe plus DE. That's phi east. Then I would have plus 0 phi west. There is no phi west in the whole equation. Plus 8 D over 3 plus F. I think it's F east. I'm just double checking that. That's the SU term. So this will be the where is that coming from? I'm doubly checking that. F east plus, actually that's so I have F east, F west, this multiplied, that's going to be F west actually. Then I have, that's 8 over 3, that's phi A, and I have F west, and I have 2 over 8 F east plus, that's F west, plus 2 over 8 F east, that's multiplied by phi A. Then you have to readjust these terms to match what's happening here. You're going to end up having the following equation. You will have, let me write down the final form, because it's going to take a few seconds to just find the equation. So I got the following equation here. I got this is the equation I end up having is AP phi P equal A east phi east plus 0 phi west plus SU. What are the terms as follow? A east is equal D over 3 minus 3 over 8 F plus D, which can be combined together. And I have A west is equal 0. I have SP is equal minus 8 over 3 D plus 2 over 8 F plus another F. Then I have AP is equal A east plus 8 over 3 D plus 2 over 8 FE or F plus another F. Then I have SU is equal to 8D over 3 plus FA plus or F plus 2 over 8, another f, times phi a. So these are the coefficients that we got for node number 1. Then I'm going to collect all these coefficients at the end in one table. Then I'm going to substitute with the value of f and d to convert that into numeric. But we're looking for the more analytical methods right now. You do the same for node number 5. Node number 5, which is the last node that we need to do. This was step 3. That's now step 4, which is node 5. In this case, node 5 would be near to the right boundary. That's node 4. That's node 3. Then I have, this is now my east face. This is my west face. This is my P. This is my west, right? There's an imaginary node here. I'm going to call that node X or O, like what we put it before, right? And let's see how we're going to do the approximation here. D phi by dx on the west face is allowed to use, again, this is a linear change, right? So I'm going to use phi p and phi west divided by delta x. So that's going to be phi p minus phi west divided by delta x. But I cannot use the same approximation for the east side because the distance is delta x over 2 or delta x node, and this is not allowed in the quick scheme. So that's the first approximation. I will call that 1. Then I'm going to use the equation for phi phase equal 6 over 8 phi I minus 1 plus 3 over 8 phi I minus 1 over 8 phi I minus 2. This will be my I point. I'm looking for the, I'm going to look for the west face right now. Let's look to the west face, right? So I'm going to look to the west face. So this is going to be I. This is I minus 1. This is I minus 2. So if I want to get phi west, that's easy now. Phi west will be simply phi of the west face. That's a W small. 6 over 8 phi I minus 1, which is phi west, plus 3 over 8 phi P minus 1 over 8 phi I minus 2, which we're going to call that the west-west. So that's going to be phi west-west. Now, phi on the east face is simply phi B, which is equal to 0 actually. So it's going to be phi B. So I'm going to call this as item number 2, and this is number 3. So what's missing now is d phi by dx on the east face, which I cannot use the approximation because of that distance is not full distance. I have to derive the quadratic equation for the 3 points. Then I will take the derivative and I get the slope of that function at the east face, which will give me the value of d phi by dx on the east face. Let's do that. So if I draw, that's node 5 is here. That's P, which is node 5. That's node 4, which is node W. Then what I'm going to do, I'm going to take, that's phi B. I'm going to draw a quadratic curve here. That's phi P, and this is phi west. Okay. Now, I'm going to put, actually, this is the east face. I'm going to put the x-axis this direction here. So x here is equal 0. X here is equal minus delta over 2. And x here is equal minus 3 delta over 2. Then the quadratic equation is phi as a function of x is equal ax squared plus bx plus c. I have x equals 0. The phi at x equals 0 is simply phi b. At x equal minus delta over 2, phi at x equal minus delta over 2 is phi p. And at x equal minus 3 delta over 2, phi at that value of x is equal phi west. You can substitute with the 3 conditions here. You can easily solve. And what I'm looking for is d phi by dx, which is going to be a 2ax plus b Now I want to get the derivative d phi by dx on the east face, which means at x equal 0, which is going to be the b. So all what I need to do is to find the value of b. I got the value of b to be minus 1 over 3 delta multiplied by, no, that's actually plus, minus 9 phi p plus phi west minus 8 plus 8 phi of the face b. Let's look into this and compare that to what we got for the b before. It's kind of like negative value for everything. That's what we got here. 9 phi b. Let me compare that with this. 9 phi b. We got minus 9 phi b. This was the east side. Here I'm getting the west side. And there is 8. If I take negative sign out, minus 1 over 3 delta, I would have 9 phi b p plus minus phi west minus 8 phi b. So it looks like you get the same coefficient but with a negative value here. So that's your piece of equation number 4 that you're going to need to substitute into the main equation. You substitute, you will get the following. So I will get the equation in the form of AP phi p equal A west phi west. I got 0 in the phi east, but I got also SU. What is the following coefficient? Looks like they as follows. I have A east is equal 0. I have A west is equal to D plus 6 over 8 F plus D over 3. I got AWW is equal to minus 1 over 8 F, and I got SU is equal 8D over 3 minus F. I got SP equal minus 8 over 3 D minus FB, and I got AP. I should add A East, A West, AWW. So this would be A East plus A West plus AWW plus 8 over 3 D minus F. So these are the coefficients here. Again, I have the value of D is equal 0.5. I have the W of F is equal 0.2. So I'm going to construct the table of coefficients, collecting all of them together and see how that table looks like. So let's have the table of coefficients collected together. I have it already collected. It's going to be a big one, but it's important to have that table of coefficients. So I will say that this is node 1, 2, 3, 4, and 5. I will put the A West West. I will put A West. I will put A East. We have SP. We have SU. And we can calculate actually the AP if we need to do that, right? So let's put the values here. So AWW here is 0, 0. This is D over 3 minus 3 over 8F plus D. This is minus 8 over 3 D plus 2 over 8F plus FA or F. This SU, I'm going to maybe shift that. And we can calculate the AP at the end. That's actually 8D over 3 plus F plus 2 over 8F. And this multiplied by phi A. Then this would be 0 D plus 7 over 8F plus 1/8F. Then A East is D minus 3 over 8F. SP is quarter of F, and this would be minus 1/4 of F by A. For node number 3, minus 1/8 F. This will be D plus 6/8 F plus 1/8 F. And this is going to be D minus 3/8 F. This is 0 and 0. This minus 1/8 F. D plus 6/8 F. We know that node 3 and 4 are the same. Node 5 minus 1/8 F. Then I have D plus 6/8 F plus D over 3. This is going to be 0 minus 8/3 D. Minus is outside, minus F. Then the last one is 8D/3 minus F. I know again, F is 0.2, D is 0.5. Phi A could have phi B somewhere, which is 0 actually, right? Phi A is equal 1, phi B is equal 0. Then you can convert that into numbers. I did the conversion to numbers. I got the following numbers here, and I calculate also the AP values. So if you wanna break down that symbolic long example to numeric values, you would have the following. I have A West West. I have A West. I have actually we'll start with A West first. A East. A West West. Then I have SU. I have SP, and I have the AP value. That's node 1, 2, 3, 4, and 5. Then we'll put the values in a red pencil writing here. So that's going to be 0, 0.7, 0.675, 0.675, and 0.817. A East is 0.592. This is 0.452. This is 0.425, 0.425, and 0. Then this is going to be 0, 0, 0.025, 0.025 negative, and negative 0.025. SU, I got 1.583. I got minus 0.05. I got 0, 0, and 0. Then I got SP is minus 1.583. I got 0.05. I got 0, 0, and minus 1.133. Then I got AP is 2175, 1.075, 1.075, 1.075, 1.925. These are the numeric value. I can now construct the coefficient matrix. Again, I'm going to draw a guideline for myself. So I have 1, 2, 3, 4, 5 values. I have 1, 2, 3, 4, 5 values. Okay. Diagonal is my AP. So that's going to be 2.175, 1.075, 1.075, 1.075, 1.925. Then I will take the first line. We have A West is 0. I have A East, right? That's minus 592. Minus 5.592. Remember, we add that negative sign, right? From the for the values in here. Then the rest will be zeros. Go for node number 2. I have A East is minus 0.452. That's West 1, that's minus 0.7, sorry. And the East is minus 0.452. Then everything is 0. Now go for node number 3. Now you will see A West, which is minus 0.675. I have A West minus 0.452. I have A west west minus 0.025. Remember, this is your P west west west, so I add that number here. I think that's actually negative. Let me double check that one. This is originally actually negative, so this would be positive here. Okay, these are typical, same. So then I will go for node number 4. I have A east, which is minus 0.425. I have A west, which is minus 0.675. I have A west west, which is going to be 0.025, and I will fill the rest with zeros. Here I will have, I have nothing on the east. I have A west, which is minus 0.817. I have west west, which is going to be 0.02500. These are phi 1, phi 2, phi 3, phi 4, and phi 5. And these are the SU values, 1.583 minus 0.05000. You solve the matrix, you can get the values of the phi. I got the values of phi from this solution to be phi 1 is equal to 0.9648. I got phi 2, it's 0.8707. I got phi 3 is equal to 0.7309. Then I got phi 4 equal to 0.5226. I got phi 5 equal to 0.2123. So this is the solution of very long example using the quick scheme. So what are the lesson learned here? Number 1, interior nodes are no longer one package. We have seen that node 3 and 4 are treated separately than node number 2, because now we need a west-west point that maybe does not exist for node number 2. That's lesson number 1. Lesson number 2, the approximation of the diffusion term works nicely with the central differencing scheme for the interior nodes. But when it comes to the boundary nodes, you have to develop a new quadratic equation for the west side on the left boundary point and to the east one in the right boundary point. So that's one thing to be careful about when you solve using the quick scheme. I know that has been a little bit of a long example, but it is very important how to know how to apply the quick scheme. If you open your star CCM code that you use for numerical analysis, CFD code with finite volume method, you will find that quick scheme is already exists. Upwind scheme is also used, but quick scheme is giving us more accurate results for many reasons that we discussed during the approximation of that technique. And that's conclude that recording for this example.